Good morning. This is the video for 9D Chem, and it's the 13th of May, and we're going to work with potential energy diagrams today and see what a catalyst does. And if we get there, we'll talk about kinetic energy diagrams too. So I'm going to hang out here until people show up, and we'll begin once a bunch of folks get here. I see I got a couple already. Victoria, and Emma, and Aaron are here. Welcome, you three. Natasha and Rhea are here. Thanks for joining us. People are flying, and that's great. Maybe one of the boys will join us too. We'll see. Yeah, so I think I'm going to pull that down a little bit. You can see the whiteboard a little better. While we're waiting, I'm going to ask you guys some review questions from last week. Get my little box, or desk as we call it, out of the way. Isabella's here. Very good. So we do something like this. And Lena's here. Great. As is Freedy. Good morning, Freedy, the first gentleman to join us. Very good. Great. Okay, so you seven, let's go ahead and take a look at one of these potential energy diagrams. So let's do this. So that was from last week. So I want you to tell me, here's the reactants. I'm going to put an R there. Here's the products. I'll put products because I got more room. So my question to warm up is, yes, I got you, Isabel. My question is, why do I got to put this energy in from here to here? Two questions. What's the energy called, and what does it do? And Becky's here. Super. So from last week, what's that energy called from here to here? And what does it do? Why do we have to put it in? It's a potential energy, yes. And yes, Aaron, it's called the activation energy. Good. So what's the activation energy do? Why do we need to put in energy? It's endothermic energy to start the reaction. Yes, good, Natasha. We're getting warmer. Lena has nailed it now exactly. Lena says you need energy to break the bonds. So all of chemistry is we got to break bonds and then we make new bonds. So exactly, Emma. So you got the old stuff, the reactants, the things you start with in chemistry. You got to break up their bonds because you got to build something new. But to break bonds, it takes energy, like you're taking apart a kit, right? I'm taking apart a model. And that's all the energy you put in. Then when you get the new bonds that are formed, that gives off energy. So you give off, in this case, it's not so much energy, but I give off a little bit to get down to the products. Okay, and somebody said it already. Good, a lot of you are participating. Thank you. Somebody said it already, but what sort of reaction does this represent? An exo or endothermic reaction? Check your notes from last week, and I'll write down that Ada is here. Johannes is here. And everybody's got it. Dynamite. Whoa, but I got people I don't even know. Carlotta's here. Hold on. Let me look and see if I got everybody else. Yes, 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 yes. Good. I'm really glad you guys are following this. Okay. Okay. So clearly this is more energy. So I have to put in energy overall. In fact, the overall amount from here to here, that's the like a net energy increase. But no one calls it that in chemistry. So I'm going to just tell you what they call it. And it's called the heat of reaction. So that's always the difference between the two platforms, right? Where the reactants are and where the products are, the heat of reaction. Yeah, so if this is higher, it's endothermic, as everybody knew, dynamite. Swelleroonie. Good. So, folks, we're going to continue with our ideas of potential energy diagrams today. And if we get that far, we'll talk about kinetic energy diagrams. But that's a little different animal. Let's see here if there's anything else I can ask you. Yeah, just in general, if you weren't here last week, yeah, right here. Okay, so what is chemistry? I'm going to say in a word, chemistry is two things. We got to break bonds of reactants. And that requires energy. En for energy. Then we form new bonds of products. I'll say that in the products. That's a U there. And that releases energy. Okay, so if you want to know what chemistry is in a nutshell, that's it. Okay, chemistry, we break bonds of reactants always. You can't do anything till you do that. That requires some energy. Then we form bonds in products, and that releases energy. It's just a question of what's more. Okay, do I got to put more in, like here, more to break up the reactants, or is it exothermic? Do I have to put in less to break them up, and then I get a lot back when I form the new bonds of the products that releases energy? Okay, anybody else new here? Let's see how many I got. I got Natasha, I got Becky, Isabel, Johannes, Aaron. I got Ada, Friedi, Lena, Carlotta, Emma, Rhea, and Victoria. Let me know if I didn't call your name, okay? Righto, good. Questions from you about this? I'm going to change boards as soon as I think you've had a little time to write that down. I mean, really, do any of your other teachers have two whiteboards? I went all out for you guys. Okay, then let's change that. Ready and shaboom. Whiteboard number 2. You'd. Okay, good. I want to do another PE diagram. PE is short for potential energy. That's this type of diagram is called. And I think I'm not going to put the axes labels. Is that okay? Because it's the same sort of diagram, okay? So I'll just say PE here. Reaction. All right, I changed my mind. Reaction steps, we'll call it. Okay. So I'm going to do a another diagram here. Boom. 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 And of course, that's where my reactants are. That's my products. You might say, Mr. Weiss, what are you doing? You just drew that. I know. But I got to ask another question about this. I'm going to tilt that. You can see a little bit. So it's another endothermic diagram, right? Okay, fine. But here's my question. What happens here in the diagram if we add a catalyst? Okay, quote, quick reminder from 2 weeks ago. Catalyst, these are chemicals that you put in and they speed up the rate of a reaction, right? But they're not used up themselves. So they're left over afterwards and you can use them again and again and again. Right. So what happens if we add a catalyst? And already I got from Carlotta, we need less energy. Good. So how's it going to change the diagram? It might turn exothermic. That would be unusual, Freedy. I've never heard of that. But yeah, probably not in this case. Less energy is necessary. Good. Maybe the curve is steeper. Okay, so my question now is, you're right. Okay, it's going to change my amount of energy. What's going to change on the diagram here if I add a catalyst? Is it going to be where the reactants are, where the products, or something about the bump? What's going to change if I add a catalyst? Let's see if you can guess. Natasha's got it too. It takes less energy to start the reaction. So how do I show that? Rhea says the diagram is less bumpy, and the bump, yes. Okay, so here we go. Let's let this be here. So my black line here was without a catalyst. Let's let this be better contrast for you. So I'm going to let the red line, a red dash line, be with a catalyst. Okay, turns out a catalyst doesn't change either the position of the reactants or products. So I don't think, Freedy, I'm going to get this thing to be exothermic. I've never heard of that happening. But what it does is it changes this. Instead of having now go up to way here, whoo, that'd be a lot of activation energy, right? Instead, maybe I can do this. Oh, it's like a shortcut. Can you see that? Can I make it darker maybe? How cool is that, huh? So it's sort of like a little activation energy tunnel, isn't it? So with catalysts, it's less activation energy. Needed. Cute, huh? Yeah, that's how that diagram changes with a catalyst. Good. Questions from you while I erase board number 1. I hope you can see that. I kind of try and tip it now and then so you can see what I've written there. All right, get erasing, Mr. Weiss. Come on, let's get the program going. All right, we got a clean whiteboard. Here we go. You good? I guess we're good. Change whiteboards. Okay, we're going to draw 4 potential energy diagrams, and I want you to try and draw them just like I do. We're going to call them A, B, C, D, and then I'm going to ask you some questions about them, all right? Okay, so I got to draw these really carefully. All right, A, B, C, D. D is a little short, but I guess you'll see all those okay. All right, so let's see how I want to do this. Okay, so we're going to go hmm, hmm, hmm. I'm going to do hmm, hmm, hmm. I'm going to do hmm, hmm, hmm. And we're going to do hmm, no, no, I'm going to do here. Hmm, hmm. And okay. Okay, so try and draw those four just as I have, okay? So we got now this one, okay, it's got a little bump, medium bump, big bump, kind of a smallish bump, and then put the levels where on the other side, okay? All right, then I'm gonna ask you several questions and I'll take different people to answer different questions, okay? So these are all the same thing. These are all potential energy and stages of the reaction. Stages of reaction. Okay. Reactants, products. But they're all the same, all right? So I'm not going to write that over and over and over. Okay, so which are endothermic, exothermic, put in order, fastest to slowest. Put in order, fastest to slowest for the reverse reaction. And finally, which has the most stable product. Okay, now let me get out of the way and I'm going to tip this a bit so you can see it. And I'm going to read them off one by one. And you might say, Mr. Weiss, we haven't done that before. That's right. That's why we're going to do it now. So I want you to take some educated guesses. Okay, everybody guess on all four of them. If you're wrong, it doesn't matter. We're going to do them together in a little while. Okay, but you got plenty of time here. So once you got your four diagrams, write down the four questions. Question A, Oh, I should have said 1, 2, 3, 4. Anyway, this doesn't correspond to the ones up here. It just happens to be A, B, C, D again. Okay. All right. The first question is which ones of the four diagrams are endothermic, and second, then which are exothermic? Question B is put them in order, fastest to slowest reaction. Think of what might be the what you'll gauge that on in the diagram. What will be faster than what, but I won't tell you yet. Now, the other one is put in order fastest to slowest for the reverse reaction. So pretend you're coming from the other side, the product side, and you're going then back to the reactant side, because here's what I've never told you. Reactions, many of them in chemistry go forward and backwards both. So some reactions go backwards. So see if you can figure that out. And then finally, what has the most stable product, A, B, C, or D? See if you can think of what would be stable. All right, I'm getting some answers already. I'm going to give you a little time here to work on these, and I want everybody to try and guess. So write down something for all four questions, okay? Just take a guess. If you're wrong, it's all right. Some of you got some guesses already in the first couple. That's great. We'll take your answers here in a moment. And again, I'll move this back and forth so you can hopefully see everything. Good. Okay, got some guesses for the first one already. We'll take care of that one. So I got from Freedy and others. I got endo and exothermic. Let's see. Okay, I'll look at Freedy's here for Gren. So Freedy, what do you got? You got A is exothermic. Yeah, it's looking that way. So exo would be A. Going, I'm losing energy because the products are lower. And then I've got to Aaron. Aaron says AD or exothermic. So she says D is also exothermic. Yeah, the products are lower in energy than the reactants, so they give off some energy. So that must mean the other two are endo. Let's check it out. Notice endo, I end up with a higher energy. Huh? Tricky, huh? Look at that. I go from products to reactants, so I end up higher, endothermic. You have to put energy in. Energy has to enter the system. See, there's lots of ways to remember that. So I go from low to high energy, and those are both endothermic. I agree. And I just wrote the wrong thing. B, C. Good. I think lots of you had that, and I'm pleased that you had that. Emma had that as well, so super. Good. Remember how to recall exothermic. Energy's exiting the system. So if it's lower here, then I get extra energy and it goes off and becomes heat or something. Same here. Here I go down here, the extra energy becomes heat. And I got a new person here. Lars is here. Good morning, Lars. Super. Okay, go. So I got some guesses from Rhea. Let's get some other guesses down. I'm not even going to look yet. So the next two questions are putting them in order. Fastest to slowest. This is going in the forward direction. Forward, forward, forward. The other's going in the reverse direction. Backwards, 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 backwards. And then finally, question D, which has the most stable product? Whew, exciting, huh? Crazy. So, okay, good. We got a couple of you guessing and writing some stuff down. So be mutig and go ahead and give me your guess. Good. Thank you, Natasha. Got one from Natasha, Rhea, and Becky. Good. Let's see if some others can give me some guesses, and we'll see who's right in a moment. Very exciting. A lot has a guess as well. Okay, here we go. All right, well, let's talk about B then. Here we go. So put in order fastest to slowest. Well, if it's fast, I'm just going to pick somebody here. Let's pick Rhea and just see what she put. So she says question 2. I'm going to read her answer here, Ray. Yeah. A, B, D, C. Okay. A is going to be the fastest one. She's right about that. Let's see why that is. Compare that with the others. A is the fastest because it's got the lowest energy. So why is A the fastest of the 4 diagrams? Got the lowest energy. Thank you, Carlotta. See if some others get it too. You got it. Thanks. And Natasha and Emma, good. So let's look at the height of the bumps, right? So lowest bump, fastest. So second lowest. Let's go back to whoever answered that. It was Reyes. So I'll just put all Reyes and we'll check it. Okay, so she said A, B, D, C. A, B, D, C. A, B, D, C. All right, let's check her. Let's check and just see, okay? All right, so A, that's the shortest bump. B, that's definitely bigger. D is, oh, wait a minute. D is a smaller bump. I don't think it's going to be quite the same order. Let's take another guess. That's why we do this together. No big deal. So I agree with A. And go with the next bigger bump. So let's see who else guessed here. Let's go up to Becky. Fastest to source, BADC. No. Okay, well, B won't be the fastest. So let's see. Let's get another one here. So Ray's got a new guess, and as does Carlotta. So here we go. So the second fastest will be the next bigger bump. So that's D, isn't it? And I tried to make it really clear. The next bump, and now we got it from Becky, is she has D and C. I think we got to go back and pick somebody up. So this is fast, not quite as fast. The third fastest going to be B or C, gang. The third fastest. Yeah, going to be B. Then C is pretty darn slow. Look at the height of that bump. It's hard to achieve that energy. That's a lot of energy. So I think we got to go B, C. Okay, I don't want to lose anybody, especially because I can't see you. So let's make sure we know what's going on. So the faster, the lower that bump is. So the easier it is to achieve breaking stuff up. Or you could say the easier it is to have them bam and break up and so on. And Sam is here. Thanks for joining us, Sam. We've now doubled the number of boys in the class to 2. Okay. The ladies are ruling today. Go, ladies. Okay, here we go. So here we go. So fast, a little bit slower, really slow, a lot of energy. So C is our slowest one. Okay, for the reverse reaction, now look at it from the other side. Now we're going here, from that side back to the beginning. All right, so it's okay to change your guess. I got 7 who got guesses. Good. We got there going back, here going back, here going back. So let's see what we got. Ooh, I got some quick punchers. Let's see what Natasha's got here. So she's got B for the backwards one, the fastest. Let's see. Hey, look at that. If I'm going back, look at that little tiny hill. I think she's right. That's the shortest hill going backwards of any of them. I'm going to say that's looking good. So I got a B there. Let's see who else has thrown. Victoria says after that we got C. So let's see. B, C. Yeah, I don't see any bump that's shorter than that one on B. So C. And then she says AD. Let's check that. AD. All right, A's got this big a bump. Oh, and D's got a big old freaking bump. So the reverse reaction is going to be mighty slow. Now, isn't that kind of cool? Let me give you a practical thing here. Let's take one from biology and medicine. Every reaction in the universe has a diagram like this, and they usually have numbers, okay? Energy in kilojoules over on this side. That's the where you got the number, okay? What's cool is this can tell you what's going on. Like, here's what I mean. Let's say I want to make some new drug to cure the coronavirus. Wouldn't that be nice? Well, if it's an endothermic reaction, I know the diagram is going to look something like this. And maybe I want to be able to make that easier. Oh, wouldn't it be nicer if I could have a diagram like this? Because there's less activation energy to form that medicine. So this is all about manufacturing things for human beings, as well as things that occur in nature. They all have their reactions too. Okay. Give you an example. If I have photosynthesis, that's probably like this. Trees take CO2 and water and they make sugar. And it takes them some energy they get from the sun. Okay. So that'd be photosynthesis. Here's a question. Which of the four, I know we haven't done D yet. I know, just hold on. D's kind of hard. Which of these four could represent lighting and burning and exploding a firecracker or fireworks at Sylvester? Which of these four could represent fireworks or a firecracker? So take a guess here. Fireworks or a firecracker? Okay. I don't think B is going to work because I would have to end up with more energy than I gave off, so it wouldn't be much of a firework. C is not going to work because if I have a firecracker, if I explode it, it's certainly not going to be more energy when I'm done. What about A? This was Aaron's guess. So Aaron, explode that sucker and bam, gives off a lot of energy. Oh, yes, indeed. Or could be D too, could it? Bam! And then gives off a lot of energy. The energy we see as light, we hear the energy, right? Sound, and heat is given off, so all these suckers are given off. So either A or D could be a firecracker, because definitely a firecracker would be an exothermic reaction, wouldn't it? Yeah? Cool, huh? Okay, let's go to our last question. And although it's an odd question, it's really important for industries. So, which has the most stable product? So which product, once I make it, is probably not going to go backwards? Which product, once I make it, is not going to go backwards? Ooh, good. I got some folks already on it. Yes. Oh, good. Dynamite. Everybody's got it. Good. So the answer is the one that has the biggest activation energy from the product side. So look at this. Look at this thing. Whoa, if I make this stuff, there's no way in you know where that this is going to go backwards unless I have a lot of energy in the reverse direction. That'd be unusual. So everybody's got it here. Good. So D would be my most stable product. What's the most unstable product? A, B, C, or D? Probably not D, right? So what's the most unstable product? And we'll talk about why that's a problem. A, B, or C? What product would not be very stable? Sam's in there, and so is Becky, and a bunch of people. Natasha, very good. So it is definitely B. Let's talk about why that's a real concern. Let's say you're a manufacturer and you're making a medicine. Well, if I have to have this endothermic reaction and make the medicine, the problem is the medicine molecules can bump into each other and very easily achieve the energy to go backwards and break apart again. So sometimes what people have to do in industry is once a chemical is made, and it could be iron, it could be a medicine, it could be a type of plastic, whatever they're making. If it has this sort of diagram, they've got to physically take it out of the system. Let's say my system's a big barrel. I've got to get it out of that barrel before it turns back to the reactants again. Okay? So we call that decomposition. We don't want it to, you know how a log, it can decompose. You ever hear that in biology? Falls apart. We don't want our chemical to fall apart if we want to use it. Case in point, there's an explosive. If I have you next year for 10th grade chemistry, we'll talk about how to make this explosive. Not at home. And it's called nitroglycerin. Nitroglycerin kind of looks like this as a diagram. It's really unstable. So what they do is they take it once they make it and they cool it down. And if they cool it down, the molecules can't do what as much? Why do they cool things down if they got an unstable product? What can't the molecules do as much? Why would I cool down my unstable product? Mm-hmm. Yeah. Yeah. We don't want them to collide. So Carlotta has it, or react, right? Aaron, good. We don't want them to do this. And if they're going faster at a higher temperature, they're more likely to do this. We want to have them cool down. So even if they collide, it's like gentle bumps. Boop, boop, and it doesn't really do anything. So that's the scoop ski. Good. Questions from you. Let me pause here and flip this so you can maybe see it without so much glare. Can't collide as often, right, Lena? So any questions about these sorts of diagrams, potential energy diagrams? They're really powerful in chemistry. Really useful. As are the next ones that we're going to talk about. Okay? We good? All right, then. Let me erase the other board while you guys are thinking. If you got any questions, let me know. Try and read your online thoughts over there. Okie dokie. Well, that was all about potential energy diagrams. What we're going to start now and work on next week or whenever I see you again are called kinetic energy diagrams. Okay, kinetic energy in chemistry and physics is known as Ke. Ke. So what is kinetic energy? Who's had it either in chem or physics? What is kinetic energy to start out with? We'll show you a diagram in a second. We're talking about molecules, okay? What's the kinetic energy? What is it? What is it about molecules we're thinking about? Okay, Rhea says moving energy. Yeah, good. So kinetic energy. Carlotta says different states of matter. It causes different states of matter. Yes, it can. The more they're moving, yeah. Let's go back to Rhea's answer though. So kinetic energy. Kinetic energy is energy of movement. Now, you and I, if we're jumping around, right, we got a lot of kinetic energy. If we're dancing, we're running, whatever, we got a lot of Ke. Well, it turns out particles can too. And that's what we're interested here in today in chemistry, right? I got slow moving particles. They've got very low kinetic energy. I got ones that are moving so fast, we can't even imagine how fast they move. Particles can go really quick. So that would be high kinetic energy. So here's the diagram, our first one anyway. We're going to go, and we're going to call this the kinetic energy on the x-axis this time. How are we doing? We're doing okay. Kinetic energy of the particles. Just to make it really obvious what we're talking about. How fast they're moving, okay? Kinetic energy of the particles. Well, the other is going to be the number of particles. And we could be saying molecules here too. I don't really care which word you use for this discussion. So number of particles, kinetic energy of particles for the y and x axes. Good. All right, let's say we've got, do I have a container? I do. Here's my cup of tea, okay? So inside, I got lots of particles. They're all moving, but they're not all moving at the same speed. So I got some that are moving really quick by luck. I got some that are moving slower by luck because it's a really chaotic world. They're bouncing into each other. And I got probably a lot in between. So let's draw that. So kinetic energy. So I've got low kinetic energy here. I've got high at this end. So let's say, okay, I've got a few molecules that are got low kinetic energy. I've got more that got energy in the middle, a lot of those, and then I've got some that have high energy. That's a really typical, ready, here's the word, distribution of molecules. Distribution of, well, I guess I call them particles. Based on their KE. So what's this say? Okay, this has a bit to do with a math called statistics. This says, hey man, I've got just a few that are really moving fast. I got a few that are slow, and I've got the most particles that are in the middle. That's why the bump is highest there. Notice this diagram is entirely different than the other one, isn't it? It's really totally different. So you got to really start from scratch. This time the bump has to do with the number of particles. Lots of particles, very few slow ones, very few fast ones. We good? Okay. And you might say, well, Mr. Wise, what do I care if these particles are moving slow or fast? I do not care. Well, I know you don't care, but you might want to care because what if they're moving really slow? Ready? Here are these guys. Even if they collide, boom, boom. Are those collisions going to be very effective? Is it going to be enough to break those suckers up? Remember, we got to break bonds. Low kinetic energy. Is it going to do anything? Boom, boom, boom. Low kinetic energy. Is it effective at breaking up bonds? Clearly, no. Thank you. Lots of you for answering. Thanks, Johannes. Good. Good. I got 3 gentlemen now. So, high energy, bam, 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 bam. These particles are colliding. They can probably pretty easily have the activation energy to react, okay? Thank you, Rhea, for that comment. I will not do that. Thank you very much. Okay. Okay, so then here we go. Let's put a line on here. So let's imagine that we got particles that once they hit a certain kinetic energy, they got enough energy to react. So I'm going to put an imaginary line here. Let's say it's right here. And let's say that our time is over. Okay, so we're going to continue our diagram next week. I'll figure out when we're going to meet because I know we've got a couple days off. Everybody, thanks for joining me. And by gosh, we wish you good health and we hope to see you next week. So we'll continue there with kinetic energy diagrams. Bye-bye.